Hey, welcome to The Explainer. Today, we are going on an incredible journey, tracing the evolution of geometry. Now, this is a story that literally starts with people drawing lines in the dirt to measure fields, and it ends with us mapping the very fabric of the cosmos. It's a wild ride, and it's the story of one of the oldest and most essential branches of mathematics. When you really boil it down, geometry is just the language we came up with to describe the space we live in. I mean, think about it. It gives us the words and the rules to talk about everything from a single, tiny point all the way up to the mind-bending scale of the universe. It's the framework we use to make sense of the physical world. And you know, the name itself gives the game away. It didn't start in some lofty, abstract thought experiment. Nope. It came from a super practical need to measure the world. Geometry. Literally, earth measurement. This was a tool that was born out of pure necessity. All right, so here's how we're going to break this down. First, we'll look at the real-world problems that got geometry started. Then, we'll see the game-changing leap to abstract proof in ancient Greece. After that, we'll watch as that certainty gets completely shattered. And finally, we'll explore how geometry became the language of our entire modern scientific reality. Okay, so let's rewind thousands of years. We're in a world where geometry isn't some class you take in school. It's a vital tool. This is all about survival, building things, and holding on to power. It's about solving the immediate, tangible problems you face when you're trying to build a civilization. What's so amazing here is that you've got all these different cultures, mostly working on their own, all figuring out really sophisticated geometric rules just because they had to. The Egyptians needed to resurvey land every single year after the Nile flooded. The Babylonians were meticulously tracking the stars. The Indians were building these incredibly complex altars for rituals. And they all figured out powerful geometric truths, like the Pythagorean theorem, not through abstract proofs, but just by trial and error. It just worked. But then, everything changed. A real revolution happened. And it wasn't about fighting new formulas. It was about a completely new way of thinking. The Greeks looked at this collection of practical rules from other cultures and asked a simple but world-changing question. Why? And this slide just nails the difference. It's like knowing a recipe works versus understanding the chemistry that makes it work. The Babylonians knew that if you have a triangle with sides 3, 4, and 5, you get a perfect right angle. The Greeks wanted to prove from the ground up why the Pythagorean theorem had to be true for every single right triangle everywhere for all time. This is really the birth of what we think of as mathematical rigor. So you can think of these guys as the architects of this whole new logical structure. Thales. He laid the foundation by using deduction. Pythagoras and his followers took it to another level, basically turning number and shape into a philosophy. Then Eudoxus gave them the tools to handle tricky things like curves and volumes. But it was one man, Euclid, who managed to pull all of these threads together. And this is where Euclid's real genius shines. He didn't invent all of geometry from scratch, but what he did was give it this rock-solid logical foundation that still defines math today. He started with just a few simple definitions and self-evident truths called axioms, and from there, he built an entire system, logically proving hundreds of theorems. For more than 2,000 years, his book, The Elements, wasn't just a textbook on geometry, it was the textbook. Now, for the next 2 millennia, Euclid's geometry wasn't just seen as a mathematical system. It was considered the one and only true description of the space we live in. It was absolute. But then, in the 19th century, a few brilliant mathematicians, guys like Gauss, Belia, and Lobachevsky, they dared to ask a radical, almost heretical question. See, this one rule, the parallel postulate, it always felt a little different, a bit clunky compared to the others. For centuries, people tried to prove that it had to be true based on the other axioms. But the big breakthrough in the 19th century was to just stop trying to prove it. Instead, they did something crazy. They just assumed it was false, and then they sat back to see what would happen. And that single act of defiance blew the doors open to whole new mathematical universes. And just look at what happened. This table shows how by just tweaking one rule, you create these completely different but totally consistent worlds. In hyperbolic geometry, which is kind of like the shape of a saddle, parallel lines actually spread apart, and the angles in a triangle add up to less than 180 degrees. In elliptic geometry, think of the surface of a sphere, there are no parallel lines, and triangles have more than 180 degrees. All of a sudden, geometry wasn't one single truth anymore. It was a whole family of them. So once geometry was freed from the shackles of our everyday flat space intuition, it just exploded. It evolved from just describing physical space into this incredibly powerful and flexible language that could be used to describe almost anything. Okay, so here's a huge step that actually happened before all that non-Euclidean stuff. By putting shapes onto a coordinate grid, Descartes and Fermat built a bridge between two totally different mathematical worlds, geometry and algebra. All of a sudden, you could solve geometry problems using algebra, and you could visualize algebraic equations as shapes. This fusion was absolutely critical for the development of calculus later on. Okay, so building on these new types of geometry, guys like Gauss and Riemann developed the tools to study the very idea of curvature itself. And this is the amazing part. Just a few decades later, this super abstract, purely mathematical idea of curved space turned out to be the exact language that Albert Einstein needed for his theory of general relativity. His big idea? That matter tells space-time how to curve, and that curvature is what we feel as gravity. Mind-blowing, right? So things are getting pretty wild, and this next idea kind of pulled it all together. Felix Klein came along and said, look, what really defines a geometry isn't the shapes themselves. It's the rules, the transformations that you can do to the shapes without changing their most important properties. So in Euclidean geometry, that's things like sliding or rotating a shape. For another type, it might be something else. The key insight was symmetry is what defines the geometry. It was a brilliant way to see how all these different systems were related. And that brings us to today. Geometry has branched out into dozens of specialized fields, and each one is a rich universe of its own, way beyond anything the ancient Greeks could have ever dreamed of. Okay, so in topology, a coffee cup and a donut are basically the same thing. Why? Well, because you can squish and stretch a coffee cup into the shape of a donut without ever ripping or tearing it. They both have one hole. Topology doesn't care about distance or angles, just fundamental properties like connectedness and the number of holes. This is where we use the most abstract tools from modern algebra to understand the structure of really complex geometric objects. And the applications are just incredible, from proving centuries-old math problems like Fermat's last theorem to things like modern cryptography and even string theory. Manifolds are a huge concept in modern math and physics. The easiest way to think about it is to think about the Earth. If you're standing in a field, it looks flat, right? But zoom out, and you see it's a sphere. A manifold is just that same idea, but generalized to any number of dimensions. It's a space that looks flat up close, but can have a really complicated, curved shape overall. This is the fundamental idea we use to describe the shape of our universe. And seriously, modern geometry is everywhere, even if you don't see it. The amazing graphics in a video game? That's computational geometry. Figuring out the best way to pack things in a box? That's discrete geometry. And the search for a unified theory of everything in physics? That relies heavily on fields like complex geometry. From the most practical tech to the most profound theories, geometry is more important than ever. So, when you look back, the story of geometry is really the story of math itself. It started as a tool to measure the ground beneath our feet, and it transformed into a language that lets us describe worlds we can't even see, helping us tackle humanity's biggest questions about space, time, and reality. And that's really the question, isn't it? As we keep pushing the boundaries of what we know, the language of geometry will keep evolving, right there with us, ready to describe the next layer of reality we manage to uncover. It's a pretty profound thought. Thanks for joining this explainer.